In this lecture, we explore functional programming, a style of software development that treats functions as first-class values and avoids mutation. We cover first-class functions, the iterator pattern, generators, and the map, filter, and reduce operations. By the end of this session, you should understand what it means for functions to be first-class values and how to write function-type expressions and arrow functions. You should understand the iterator pattern and its mutability pitfall, and how generator functions implement iterators cleanly. And you should know how map, filter, and reduce replace imperative loops, and how they connect to SQL. A value is first class if it can be stored in a variable, passed as an argument to a function, returned as a return value, and created dynamically at runtime. In TypeScript, functions are first-class values, treated exactly like numbers or strings. We can assign math.sqrt to a variable. We can call the variable just like we would call math.sqrt directly. This one idea, functions as values, unlocks a dramatically different way of writing software. Every function in TypeScript has a type that describes its signature. Math.secretQuarter has type, a function from number to number. We write this as an arrow in the type, open parent x:number, close parent arrow number. There is an important syntax rule. The parameter name is required inside the type expression. Writing just number, arrow, number is wrong. TypeScript treats the bare number as a parameter name of type any, not as the type itself. Functions can be defined without a name as expressions. A named function statement uses the function keyword followed by the name. An anonymous function expression uses the function keyword without a name assigned to a variable. An arrow function is the most concise and idiomatic form, just the parameter list, an arrow, and the body. All three behave identically in most contexts. Arrow functions are the modern choice. Arrow functions have a concise form for single expression bodies. If the body is a single expression, you can omit the curly braces and the return keyword. Open parent x:number close parent arrow x times x. The x times x is implicitly returned. There is one technical difference from function expressions. Arrow functions capture this from the surrounding context. Standard function expressions create their own this binding. This makes arrow functions safer inside class methods and callbacks where this must refer to the class instance. To understand what is first class, it helps to see what is not. Access control keywords like private and public are not first class. You cannot pass them as arguments. Control structures like while loops and if statements are not first class. You cannot store them in variables. But you can pass a function that encapsulates that logic. You can store the predicate, the transformation, the accumulation, all as first-class function values. Functional programming moves logic from inside loops into first-class function values. Traditional programming uses explicit control statements for loops, if statements, accumulator variables. The goal of functional programming is to operate on sequences with no explicit loops, no explicit conditionals, and no mutation variables. Instead of describing how to iterate, you describe what the computation does. The pattern of summing even numbers becomes: filter the sequence to keep only even numbers, then reduce by addition. No loop, no index, no if statement. Just what? An iterator is an object that steps through a sequence one element at a time. The next method returns an object with two fields, done, a boolean, and value, the current element. When the sequence is exhausted, next returns done, true. Iterators provide uniform access across arrays, sets, maps, any collection. The key benefit, traversal logic, is decoupled from the collection's internal structure. There is an important property of the next method. It is a mutator. Calling next advances the iterator's internal position. It permanently consumes that element. Once an iterator is exhausted, it cannot be reset. To iterate again from the beginning, you must get a fresh iterator from the collection. This mutability is a source of bugs when iterators are shared or reused unexpectedly. It is important to distinguish an iterable from an iterator. An iterable represents an entire sequence, a whole array or set. Its key method is symbol.iterator, which returns a fresh iterator. An iterator represents a position within a sequence. Its key method is next, which advances and returns an element. Design advice: use iterable of t in function signatures, not iterator of t. A function receiving an iterable can create a fresh iterator whenever it needs to. A function receiving an iterator has no way to restart. The position is already partially consumed. Mutating a collection while iterating over it produces silent bugs. This function tries to remove all TypeScript files from an array by calling splice inside a for-of loop. But splice shifts all subsequent elements left. The iterator does not know about this shift. It skips the element that was shifted into the position of the removed element. Files are silently missed. No error, no exception, just incorrect behavior. Fix collect items to remove in a separate array, then remove them after the loop. Or use filter. Functional programming largely avoids mutation. Mutation creates non-local contracts. The correctness of one part of the code depends on every other part that holds a reference to the same mutable object. The push example. Calling push on an array is visible through every alias. This is a hidden dependency between all holders of that reference. The functional alternative spread to create a new array. The original is untouched. Each function is responsible only for its own output. FP patterns produce new sequences rather than modifying existing ones. A generator function implements the iterator interface, producing elements one at a time using the yield keyword. The function star syntax declares a generator. The body runs lazily. It is paused at each yield and resumes when the caller calls next. This odds generator yields 1, then 3, then 5 infinitely. Generator functions are perfect for infinite sequences or expensive computations where you only want to compute as much as you actually consume. The caller pulls values. The generator produces them on demand. Map, filter, and reduce are three operations that replace explicit loops and produce new sequences instead of mutating. Map takes an array and a function and applies the function to every element, returning a new array of results. Filter takes an array and a predicate and keeps only the elements where the predicate is true. Reduce takes an array, a combining function, and an initial value and collapses the entire array into a single value. All three are native methods on TypeScript and JavaScript arrays. Map applies a function to every element and returns a new sequence of the same length. The array 1, 4, 9, 16 mapped through math.sqrt gives 1, 2, 3, 4. The array A, B, C mapped through to Lamos gives A, B, C. Map does not mutate the original. The result is always the same length as the input. The pattern for map is do the same thing to every element. Map and for each look similar but serve different purposes. .map returns a new array containing the return values of the function. Use it when you are transforming elements and collecting results. Tortoise returns void. Use it when you are triggering side effects, printing, logging, or updating external state. If your function returns void, use for each. Using map and discarding the result is a code smell. You are creating an array and immediately throwing it away. Filter tests each element with a predicate and keeps only those that pass. The array 1 through 4 filtered with the odd predicate gives 1 and 3. An array of file names filtered to keep only those ending in .ts keeps only the TypeScript files. Filter returns a subset of the original. The elements are the same type. The original is not mutated. The pattern for filter is keep only the elements that satisfy a condition. Reduce collapses an entire sequence into a single value using an accumulator. The diagram shows how it works. The accumulator starts at the initial value, here 0. At each step, the combining function receives the current accumulator and the next element and returns the new accumulator. For the array, 1, 2, 3 with addition, accumulator starts at 0. Plus 1 gives 1, plus 2 gives 3, plus 3 gives 6. The result is 6, the sum of all elements. The initial value in reduce has two roles. First, it starts the accumulation before any element is processed. Second, it is the result when the array is empty. Calling reduce without an initial value on an empty array throws a tertices. Rule always provide an initial value. Omitting it makes your code fragile and surprising when arrays can be empty. The standard reduce accumulates left to right. Reduce right accumulates right to left. For commutative operations like addition, the order does not matter. The left fold diagram shows how the accumulator grows from the left side, 1, then 12, then 123. The right fold diagram shows accumulation from the right, 3, then 23, then 321. For non-commutative operations like string concatenation, always think carefully about which direction you need. The return type of a reduction does not need to match the element type. You can reduce an array of numbers into a string. 1, 2, 3, reduced with string concatenation, gives the string 1, 2, 3. You can reduce an array of strings into a number. The total character count of cat and elephant is 11. This makes reduce a general aggregation mechanism. Sums, products, string building, counting, object construction all fit the same pattern. A higher order function takes a function as an argument or returns a function as its result. Map, filter, and reduce are all higher order functions. Hoffs enable dynamic logic generation. The ends. With function here takes a suffix string and returns a predicate, a new function that tests whether a string ends with that suffix. We create STs as a specialized predicate, then pass it to filter. This is parameterized behavior. The logic is captured in a value and passed around. Functional patterns enable complex recursive tasks with minimal code. This function collects all files in a directory tree. It spreads the files directly in this directory, then maps over subdirectories, calling files ein directory recursively on each one. Flatmap combines map and flat. It maps and then flattens one level of nesting. Map and flatten is so common in functional code that it has its own dedicated method. Here is a larger pipeline, extracting all alphabetic words from TypeScript source files in a project. Step 1. Filter to keep only .ts files. Step 2. Flatmap each file to its lines. Step 3. Flatmap each line to its words, splitting on non-word characters. Step 4. Filter to remove empty tokens. Step 5. Filter to keep only words starting with a letter. 0 explicit loops. 0 if statements. 0 temporary mutation variables. Abstracting out control produces shorter and simpler code by letting you focus on the heart of the computation. It eliminates loop indices and bounds checking, temporary accumulator variables, if-else branches scattered through loops, and manual push and splice calls. This is not just a style preference. Google's MapReduce applies this same paradigm to process petabytes of data across thousands of servers. The pattern that cleans up a small for loop also underpins some of the largest data processing systems ever built. Idiomatic modern TypeScript avoids for loops in favor of method chaining. When you need to transform each element, reach for map. When you need to keep only matching elements, reach for filter. When you need to collapse to one value, reach for reduce. When you need to transform and flatten, reach for flatmap. For testing, some checks whether any element matches, and every checks whether all elements match. If you find yourself writing a for loop, ask, can map, filter, or reduce express this more clearly? Usually the answer is yes. The map, filter, and reduce paradigm is the foundation of relational database queries. Consider this equal query. Select file name and length of content from files where file name like %.ts order by length descending. The where clause is a filter. The select column is a map, projecting and transforming each row. The aggregate functions mx, sum, and count are reduce operations. Learning functional programming teaches you to think in the same way that databases think. The patterns are identical, only the syntax differs. Let us summarize the key concepts. First-class functions. Functions are values. Pass them, return them, store them. Pure functions. Output depends only on input, with no side effects. Map. Transform every element. The result is the same length as the input. Filter. Keep matching elements. Same type, possibly shorter. Reduce. Collapse to one value using an accumulator. Immutability. Produce new sequences. Never mutate existing ones. To conclude, functional programming strengthens all three of our core goals. Safe from bugs, immutable data, and pure functions. Eliminate the entire class of bugs caused by unexpected mutation across aliases. easy to understand. A chain of filter, map, and reduce reads like a description of the computation, what is done to the data step by step. Ready for change. Each step in the chain is independent. Changing one filter or map does not require rewriting any surrounding logic because there is no surrounding loop.